Subir, go ahead.
Okay, thank you, Ahmed. Yeah, so the audio from you was breaking up. I don't know, can you all hear me okay? Can you let me know?
Yeah, we can hear you well.
Philip?
Yes,
Okay,
Subir.
all right. Well, thank you for the kind introduction. Okay, thank you for the very kind introduction and the invitation to speak here. I am, of course, I'd love to be there in person. I've been to Los Alamos a couple of times, I think. But hopefully we can keep this informal, and please feel free to interrupt with questions, and I'm happy to, because I'm not entirely sure of who the audience is. All right, so my purpose today is to give you kind of a status report on progress on the theory of non-Fermi liquids. There's been, I think, a lot of interesting progress in the last few years, building on what's called the SYK model, which I'll describe. And this also turns out to have connections to the physics of black holes. And I'll also hopefully have a few minutes to say a little bit about that towards the end. So, okay, so let me begin by just defining terms. What is a non-Fermi liquid? It's a term that came into vogue around the 80s and is used freely, especially by experimentalists. And among experimentalists, what they mean is a regime of a metallic system, like here's the iron arsenide superconductors, that has a regime of temperatures and carrier concentration where the resistivity, instead of having the t-squared dependence, so that is conventional for a Fermi liquid, which is what you see here at high values of x, has an exponent which is closer to 1, and this regime over here. Furthermore, my attention really will be focusing on what's more precisely called the strange metal, where this linear T resistance goes down to very low temperatures, much lower than any characteristic energy scale in the microscopic Hamiltonian. There's another regime at higher temperatures, which is sometimes called the bad metal, where the resistivity is quite large, and also linear in temperature. That I think is better understood, and so I won't really be talking about that. I'm really talking about a strange metal, which is what happens down to low temperatures. And this is very common. It's not only seen in the arsenides as in this plot, or in the cuprates. Sometimes it doesn't seem to be this kind of fan-shaped region, but what's called a foot, where there seems to be a phase at very low temperatures with non-Fermi liquid-like behavior without the t-squared exponent. This is lanthanum, strontium, copper oxide, one of the high-temperature superconductors. Okay, so that's kind of an empirical, experimental discovery of non-Fermi liquids. What do I mean by a non-Fermi liquid theoretically? So, the objective here is to at least have some examples theoretically that we understand completely. And so we have to define what we mean. So I'll tell you what my definition is. So my definition is a state of quantum matter at very low temperature, which has two basic characteristics. One is that it's compressible, meaning that by changing a chemical potential, you can change the density continuously at 0 temperature. Okay, now I'm willing to be at slightly non-zero temperature because what could often happen is the system to go superconducting or something at very, very low temperatures. I won't be worried about such fine points. But I should note that, Dirac fermions, Weyl fermions, conformal field theories in higher dimensions are not compressible by this definition, because the density of states at the Fermi level vanishes as you approach the Fermi level in those cases. So that's characteristic 1. The characteristic 2 is that the usual Landau Fermi liquid description, which I think most generally stated in system with or without disorder, is that the low energy many particle systems, many body eigenstates, cannot be identified approximately in terms of a set of quasi-particles. So you have some quasi-particles of energy E alpha, N alpha 0 or 1, And you can write down all the interesting low-lying many-body states and view them as a set of quasi-particles. The energy could depend on the interaction between the quasi-particle, but still it's labeled by the quasi-particle themselves. And this is, in fact, almost universally true in Fermi liquids, but also in more exotic states like Luttinger liquids, fractional quantum Hall states, many spin liquids, all of the Kitaev spin liquids. They all have some set of quasi-particle excitation, which are not, may not be electrons, but still they're quasi-particles. So we don't want quasi-particle excitation. So this is also quite restrictive. In fact, once you put these two requirements, there's essentially, until recently, no solvable model which satisfied both these requirements. Okay, but experimentally, how would you detect that there are no quasi-particles? Of course, you could measure the spectral function, but that, in fact, only tells you that there are no electronic quasi-particles. There could be other types of quasi-particles from a spectral that you don't see in a photo emission experiment, for example. You could measure transport, and that's typically the easiest way, really, of course. So in an ordinary metal, when you have quasi-particles, the reason they're quasi-particles is because their scattering time is quite long. And if you ask how long is it, long compared to what? And then you quickly see that there's a natural time, which is just set by the temperature, which is h bar over kT, which now is referred to as Planckian time because it only involves Planck constant and the absolute temperature. And any system with quasi-particles, the scattering time or the lifetime of a quasi-particle has to be bigger than this Planckian time. So another, conjecturally equivalent definition would be if you have a system which has some kind of characteristic thermalization or equilibration time, which is equal to or shorter than this, then you don't have quasi-particles. And in fact, there's a conjecture that I made a long time ago that it can't really be shorter than this. This is kind of a lower bound, this Planckian time. And that's satisfied by all the models that I'll talk about. So here's a more recent experimental measurement of 1 over tau. This is from the transport. You measure the resistivity and somehow convert through the usual Drude expressions, the resistivity for various high DC and other materials to a scattering time tau. And you find the low temperatures in all of these materials near this optimal doping. That's the doping here. That it's linear in temperature. The 1 over tau is linear in temperature. And also this coefficient here, alpha, is not so far from 1. Okay. So this is then, one of the major puzzles we'd like to understand. Why do metals have this strange metal behavior where this relaxation time as measured by transport is just kT over h bar. And independent of the underlying microscopic scales, for example, the energy scales in this organic compound is at least an order of magnitude difference from, say, LSCO. Okay, and we want to understand, why this happens down to very low temperatures. At higher temperatures, above the Debye temperature, you can also find similar regimes, but that's not the focus of my discussion. So here's another recent observation by Brad Ramshaw and Louis Taillefer. This is by angle-dependent magnetoresistance measurements. So it's not transport directly. It's a measurement of how things oscillate as a function of angle, and from that they read off an isotropic component of the electron scattering time on the Fermi surface. And this isotropic component is again obeys this 1 over tau going as h bar over kT over h bar. All right, so that's a quick summary of a lot of experimental data. I first of all have to say clearly I don't think we have a full understanding of this what I'm going to present today is some progress towards an understanding. And certainly, I think, rather reliable progress at the level of certain theoretical models, which are, of course, not exactly the models found in experiments. So I'm going to talk about basically three models. The SYK model, of course, and I'll compare it to a well-studied random matrix model to begin with. So this model, okay, it has a complicated history, but in the form that I'll discuss it, it looks rather unphysical from the any realistic description of any of the materials I've just mentioned. The second model will be a random TJ model. In fact, this is the original way that I had originally proposed what's now called the SYK model. But this is more complicated, but more realistic. But recently, I think we made a lot of progress in understanding this somewhat more realistic model, which I'll describe. But remarkably, it turns out it captures the basic physics of SYK here also. And then finally, for a few minutes, just to broaden the audience, I suppose, the SYK model, if anything, had a bigger impact on the theory of black holes. And I'll say a little bit about that towards the end. Okay, so let me begin very simply. So here's a random matrix model where you have electrons moving on some sites of some fermions with some amplitude Tij, and all of these Tij are random complex numbers. So to figure out what's going on here, you just have to diagonalize an n by n matrix, each of whose elements is a complex number, independent random complex number. So just to show some pictures, you imagine you have some sites, you add some particles, and each particle can hop. There's an exclusion principle. These are fermions. That's important. And so this particle could hop from there to there, and so on. There's all kinds of hoppings allowed, and every allowed hopping can happen, but with a random amplitude. Now, a huge amount is known about this. I'll just show you a little bit. For example, if you want to compute the average Green's function of the electron on site I, it turns out to be a very simple Dyson equation, which you can easily obtain diagrammatically. Sigma is T squared times G. And then solving the whole, at least the density of states, becomes a simple problem of solving a quadratic equation. And you get the famous Wigner semicircular density of states of a random matrix. So this is in the limit of the matrix going to infinity. If you had n by n matrix, then of course you have a set of discrete levels, and the average spacing between these levels is 1 over n. Okay. And so in the many-body system, you just fill up all the states up to the Fermi level, and that pretty much describes this random matrix model. Okay, so hopefully that's all very, very familiar. And I should say, this kind of random matrix model, artificial as it sounds, has been very successful in describing experiments on quantum dots and fluctuations of conductance of quantum dots. That was a very exciting, hot field about 15 years, 20 years ago. All right, now I want to think about this random matrix model not as a single particle problem, but in the many particle space. So what I'm plotting here now is the many body density of states. So what I mean by that is you take a set of occupied states, which is of order n. So n alpha is either 0 or 1, and the number of possible EI in the grand canonical ensemble is 2 to the n, because you have n eigenvalues, and either of which can be occupied or not. So now you have an exponentially large number of eigenvalues, not of order n, as that's E alpha, but e to the n, or 2 to the n. Okay, so you can ask, what is the density of states of this? So this is just obtained from the Wigner distribution just by occupying all the states, and here's a plot of it. Surprisingly, there is actually relatively little known about the shape of this curve, especially in its tails. But in the middle, it's easy to see that this many-body density of states is just e to the entropy, which you can compute by the usual Sommerfeld expansion of a Fermi liquid. And so that's exponentially large in n. So the density of states is exponentially large in n in the middle of the spectrum. This is for the case of the Fermi energy, like I showed you here, is somewhere in the middle of the band. So the tails, one important thing to keep in mind, that the tails here don't have anything to do, with the tails down here. We assume this is really infinitely far away. So what do the tails have to do? The tails have to do with the fact that once you, if this is your ground state, which has energy 0 now with all of these states occupied, then the first excited state would be you add a particle just above the Fermi level, or you remove a particle from just below the Fermi level. And those are the states that you see in the tails. So these are the states here, which are just adding and removing particles above and below the Fermi level. Now, the important point is that the spacing between those levels, as I already mentioned, is 1 over n. So the density of states in the tails is not e to the n, it's just n, because the spacing is 1 over n. And really, the fact that the density of states is so small compared to the middle of the band, where it's exponentially large, has to do, is a telltale sign, or at least a necessary condition. It's not sufficient, that there are quasi-particle excitations. Now, of course, this is a free particle system, but if you added interactions, and then it becomes much harder, of course, but we do believe that you'll have this regime of d of e over n, and there'll be some new renormalized quasi-particles that will give you the low energy states. All right, so now let's go to the more interesting model, the SYK model, which is similar in the sense that all the matrix elements are all random, but the random matrix elements are not in the one-body term, but in the two-body term, in the hopping of electrons from a pair of sites to another pair of sites, gamma delta to alpha beta. This was actually considered in nuclear physics a long time ago, but really nothing was done about it. It turns out to have a very different large n limit. So just to show you the picture, here's the n sites. You occupy them with fermions, and then now pair of fermions can move from here to there, or vice versa, and that process has an amplitude u alpha beta gamma delta, and that's just a random number, and so on. So any pair can hop anywhere, and that's what's today now called sometimes a complex SYK model. Complex because I'm not dealing with Majorana fermions. So if you do the exact diagonalization and plot the density of states, here I showed you the density of states, the random matrix model with one body hopping. And now let's do it for the SYK model. Let's first look at this here. You see the density is completely different. It's different primarily in the absence of these long tails that you had in the one-body system. There's no long tails here. Now you have this many-body density of states, which is exponentially large. Of course, in the middle of the band, that's no surprise, and it's again given by the entropy. But if you go near the bottom of the band, it's much more dense. And in fact, as we showed a long time ago, it's exponential down to energies of order 1 over n of the ground state. And so there's and in fact, this number is universal, and you can compute it, although I won't describe how that's done. And the fact that there's so many exponentially large number of energy levels down here immediately means that there is no quasi-particle decomposition, because the number of quasi-particles you have in any system is of order n, not of order e to the n. So you can't think of these exponentially large number of states in terms of rearrangements of a few quasi-particles. There's just not enough of them. And so this is then really, the first example of a solvable system which has essentially no quasi-particle description. Okay, so I won't go into the details of how this is obtained. I'll have a little bit of technical discussion in a few minutes. Among other things you can compute is also the spectral function, the imaginary part of the Green's function, if you were to do a tunneling experiment on this model. And what you find is that the Green's function has a singularity at the Fermi level. And it's actually 1 over square root of omega singularity at 0 temperature. And at finite temperature, it becomes smooth, but the scale on which it becomes smooth is independent of the strength of the interactions. So that's really the thing that when I first started working on this, that got us excited, because you now have a regime where there's a natural time scale, which doesn't depend on the interactions at all, as would be the case in a Fermi liquid. But you have this rounding with temperature or some kind of dissipative or relaxational time here, which is h bar over kt. And that just comes out of the structure of this equation, this model at low energies. Okay, so that's then a summary then of the basic properties of the SYK model and how it differs from the random matrix model. And the two take-home messages is that it has no quasi-particle description, and also it has a characteristic dissipative time, which is h bar over kt. This is also the thermalization time. I haven't shown you data for that. That's something that's been studied by us and others a lot in the last few years. And the thermalization time of the system is also of order h bar over kt. Okay. I mean, some of you are familiar with things like conformal field theories in 1+1 dimension, or various quantum impurity models, multi-channel Kondo problems. At first sight, you would say, well, yeah, this is very natural in any scale invariant theory. But in all of these solvable type conformal field theories, the thermalization time is not this. It's actually, those are essentially integrable models. This is not integrable, and this is one of the proofs of it, that the thermalization is extremely rapid. Okay. All right, maybe I'll pause for any questions at this point. A quick summary of the basic model that perhaps. All right, so then I'll continue. So part 2 is a little technical. So I asked the experimentalist to just bear with me. But hopefully the gist should be clear to everyone. So a central actor in trying to connect to experiments will be something called the time reparameterization soft mode, which originally discovered in the SYK model by Kitaev and Maldacena and Stanford, but has a much wider application. So here's just a quick, impressionistic survey of how you get to such a thing. And that, of course, the time reparameterization, should also be pretty suggestive of the connection to quantum gravity, and that's in fact how the connection is established. So we start with the SYK model, write down a path integral for it, and then you just average over the couplings. So after you average over the couplings, you get this so-called replicated path integral. And then the first thing you do is you just ignore the replicas. So to people working in spin glass theory, that'd be a very shocking thing to do. But the point is that unlike a spin glass, another property of the SYK model is that it's extremely well self-averaging. It thermalizes, and basically every site is the same as every site. There's this very negligible point-to-point fluctuations. And that's why you can just get away with that rather drastic step. Okay, and then, so once you ignore the replicas, you can, do some Hubbard-Stern-Rich type tricks on this type of averaged action. And you can write it after some tricks where you introduce these new fields, G and sigma, which are supposed to represent the Green's function and the self-energy of the electrons. But these are now bilocal fields. It depends on two times. And this is just an identity, because when you do the integral over sigma, it tells you that G is equal to this object, which is in fact what it is. So you insert this 1 in here, then you integrate out the fermions, and when the dust settles, you get an action for G and sigma. So there's an exact representation of this path integral, not in terms of the electrons. There's n of the electrons, one fields for every site, but just in terms of two fields, G and sigma. But these are bilocal fields. It depends on two times, tau 1 and tau 2. Now, this is an exact representation of the theory. Okay, so now you want to take this theory and understand something about the fluctuations about the saddle point that I just gave you some results about. So one very important property of the saddle point is that this time derivative term, the bare kinetic, kinematic term, is irrelevant. You can just throw it out. This was something already apparent to us in the very first paper in the 90s. But Kitaev and others made a very important observation on this path integral, but what happens when you throw this time derivative term out. So if you look at the remaining terms in this action, there's no more derivatives. It just has sigma and sigma g, basically polynomials of sigma. Then you can see that it has that there is a very large symmetry here. You can reparameterize time itself. So you have some time sigma, you get a new time tau, and when you express g in terms of g tilde, sigma in terms of sigma tilde, then the action is the same expression in terms of g or g tilde. So this is very reminiscent of the kind of thing you have in general relativity, where you can reparameterize space-time. There's general coordinate invariance. This is general coordinate invariance only with time. And that's a property of the theory when you throw this term out. It's not an exact property. It's only an exact property when you ignore this term. Okay, so that's basically the important observation. The other important observation is that the saddle point itself is not time reparameterization invariance. And for the simple reason that the saddle point only depends on the difference of two times. Then you can ask, what is the, you have some symmetry, approximate symmetry, which is broken, and what is the analog of the Goldstone mode associated with low energy fluctuations along the nearly flat direction? And that Goldstone mode, or near Goldstone mode, is parameterized by this function f of tau. So you take the saddle point Green's function and you reparameterization the times tau f. And so what you have to do to identify the low energy mode is do kind of a change of variables from g and sigma to f. Now there's another field phi, which I'm just ignoring. That has to do with the charge fluctuation, and there's also an emergent gauge symmetry, but just ignore it for the purpose of this discussion. So you can map this theory from the original theory in terms of the Green's function of the electrons to a new theory in terms of the reparameterization of time itself. And there's some effective action for this time reparameterization, this S effective. And there's a lot of evidence, numerical and analytical arguments on what the structure of that effective action is. So again, ignore this. It has to condense matter physicist, a highly unfamiliar form. It's what's called a Schwartzian. It's got things like third derivatives and things in the denominator, but actually, amazingly, the path integral over this Schwartzian can be done exactly because of a large degree of symmetry. And it's also totally stable. And the reason it's stable is because you have to mod out with a certain non-compact symmetry that's obeyed by the Schwartzian. Okay, so that's a lot of technicality. If you haven't seen this before, that was way too much, but hopefully you got the general idea that you can take the path integral of the SYK model and write its low energy fluctuations in terms of an effective action for time reparameterizations. Now, the remarkable thing is that the same effective action also appears in various theories of gravity, especially certain theories of 2D gravity, where you can think of this primary reprimization as representing a boundary graviton. So in addition to these gapless fermions that are present, there's a collective mode, which is the boundary graviton in this theory. When you go to finite dimensions and not just thinking about a zero-dimensional problem like this boundary graviton is really the precursor to thermal diffusion. So if you get, it's really energy fluctuations which turn into thermal diffusion in a space model with a spatial structure. All right, so that was very technical, and I apologize. But we want to now use this boundary graviton. What good is it to me as a condensed matter theorist? So one of the things you can compute, you endow this model with some spin. You put in a spin variable, and then you compute the local spin susceptibility. So this is the kind of thing you measure by momentum integrated neutron scattering on this collection of electrons. So what you find, first of all, is that the leading term is already quite remarkable. It's the sine omega. This is what's called the marginal term by Verma et al. And this emerges automatically in the SYK model. The leading term is just the marginal spectrum of sine omega. It's a discontinuity at zero temperature, but not at finite temperature. But we can also actually talk about the correction to this. So the correction to this turns out to be a linear term in omega. And this linear term is the boundary graviton. That's how you get this linear correction to the marginal spin susceptibility. It's the effect of the fluctuations of this boundary graviton. Okay. You can also take this expression and look at it at finite temperature, and then the sine omega here becomes a tang omega over 2t. And this also has a correction. Okay, and so these are then systematic predictions for the behavior of this rather artificial looking model. Of course, what got our interest already in the early 90s, I was certainly excited, and maybe a couple of other people like Antoine Georges who thought this was interesting, that this, in those days, that this kind of spectrum is actually not too far from what's seen and conjectured in the cuprates in the underdog regime. Of course, the details are very different, but anyway, okay. Yeah, and also you see the characteristic relaxation, dissipative time coming here also, h bar over kt, and this is the boundary graviton term. All right, so then so far, all our discussion has been about this seemingly artificial model, which is the simplest model without quasi-particle excitation, so well worth a thorough study. And what we've seen now, in addition to the Planckian time dissipation and the absence of quasi-particles, that there are certain corrections to the leading scaling behavior that come from fluctuations which have the character of gravity, quantum gravity. All right, so now let me talk about some more recent work on a more physical model with the random TJ model. So now I'm going to really try to motivate things from the cuprates and see how far we can get, using models which are not, which are somewhere between reality and the SYK model. So this is work done with my student Henry Shackleton, Antoine Georges at Flatiron Institute, and Alex Vitek, who's a postdoc at Flatiron, and also a group at Harvard, Maria Tikhanovskaya and Hayo Go, my students, and Grisha Tarnopolsky, who's now faculty at Carnegie Mellon. Okay, so this is a familiar phase diagram for quantum condensed matter physicist of the cuprate superconductors. again, a huge amount is going on, but my focus here is on really the strange metal, which appears near the optimal doping, and also a little bit on this pseudo-gap metal. So the pseudo-gap, I think, is better understood than the strange metal, but there's, again, a lot of controversy of what's going on there, although not so much on the experimental side. For my discussion here, in the models that I've discussed, one of the most interesting observations is this relatively recent paper by the group of Montgomery, Julien, and Paris of the observation of spin glass behavior at small doping. And this, initially it was thought present only at very small doping, but now by application of a magnetic field, a rather large magnetic field, at least on the lab scale, you can see this spin glass behavior all the way up to the critical doping where the strange metal appears, suggesting that the spin glass ordering is one of the important ingredients in this pseudo-gap phase. Okay, and P star is roughly where the strange metal becomes most apparent. Okay, now I could spend many talks going into all kinds of details on the pseudo-gap, but you don't need it for my discussion, and hopefully those who are not so familiar, really all I want you to remember is that you have in the cuprates the basic feature that as you change the density of carriers, there's a regime where there seems to be spin glass order, and right near the end of the regime, at PC or P stars, you get the strange metal behavior, which is rather reminiscent of the properties of the TJ model I've just described, of the SYK model I've just described. All right, so let me then describe another model. Okay, so the model I'm going to describe is shown here in this picture, and I'll also have some animation in a minute. So the basic model, which I think most everyone agrees has the physics of the cuprate superconductors, is this TJ model. So what does this model consist of? Well, you have some lattice. In the cuprates, you actually have a square lattice. And on each side of the square lattice, there are 3 states that are allowed. All other states are assumed to be much higher in energy. There's either an empty state, or a state with an electron-occupied spin up, or a state with electron-occupied spin down. And within these 3 states, there are 2 types of matrix elements. One is just the hopping of electrons, so that this can hop from one side to the next. I'll show you that in a minute. And there's an exchange interaction, which is antiferromagnetic, which is mostly nearest neighbor. Okay, so that's the square lattice TJ model. Here's the words I've just told you are described in these equations here. Okay, now that model is, of course, what all of us have been studying since the early days of the cuprates, now getting on 30 years. It's too hard to solve. Anyway, we know a lot's been learned especially by a lot of numerical studies in the underdog regime. But we'd like to make more analytical progress. So what we're going to do is just take these numbers Tij and Jij and let them be just independent random numbers. So that's in the spirit of the SYK model, the random matrix model seems like a natural thing to do. It might seem like too drastic an approximation. Well, the jury's out on that, I think, on the whole. But I would argue that, in fact, it's a pretty good starting point, because it seems to capture the essence of the physics. May not get all the details of the broken symmetry correctly, but I think it got a lot of the other details correct. Anyway, so this is a well-defined model, and I'm not posing a well-defined question. Forget about the cuprates. Can you just tell me something about this model? And there is, unlike the SYK model, I can't give you an answer with any degree of certainty anyway, but we're pretty confident that we're starting to understand what's going on, at least in this model. So let me just show you a few pictures. So you imagine you have a whole bunch of sites. So some fraction of them are occupied with spins that can point in any direction. So there's an SU2 rotation symmetry. in this model. And then you can have the electrons hop from site to site with amplitude T, and every one of those is a random number. And you can also have electrons exchange their spin with amplitude J, and that's also a random number. Okay, so that's the model we want to understand. All right, so we've done a lot of work on this over the years. In fact, the original model I worked on in '93 was exactly the J model here without this term present. And especially now, there's been a lot of numerical work of this model as n becomes, order 20, or actually you can even, as I'll show you, solve the model at n equals infinity, but using quantum Monte Carlo. So here's the results from exact diagonalization, where you compute this local spin susceptibility that I showed you earlier for the SYK model. So I showed you this curve here. Let me remind you. Just one here. So I had this chi of omega coming in. So I'm plotting exactly the same quantity here. It came into a constant with the sine omega in this SYK model anyway. So what you see here, okay, what you see, so this is the actual data at low doping. So P is close to 0 doping, and then P is exactly 0, and then you increase the doping. You see a large peak, which becomes larger and larger as the system size becomes larger. And that's indication of spin glass order. So the spins are freezing and just taking some random frozen state. Now that's not the SYK physics, but it's what's seen in the experiment. So okay, that's good. As I just showed you in the data, there's spin glass order. But as you increase the value of P, for a P around 0.3 to 0.4, you see that the peak disappears, and you get, say, this red line here. And remarkably, that observation in the actual TJ model at the critical point between the spin glass phase and the Fermi liquid is almost exactly the same that you observe in the SYK model. Has this, the actual model is sine omega 1 is 1 minus constant times mod omega, and that's not too far from what you see right near the critical point. When you go above the critical point, then it has a Fermi liquid form, which would be a linear function of omega. Okay. So that's appeared twice. Sorry about that. Sorry. I've already said what I want to say about these slides. And I've also recalled this. Okay. So here's another work looking numerically at the TJ model using a different method. This is not exact diagonalization. This is a quantum Monte Carlo method using DMFT tricks by the group at Flatiron. And they see as a function of density, which they call N here, not P. Indeed, you have a spin glass metal for a while, and then a Fermi liquid. And right in this regime, right near the critical point, if they measure the spin correlation function, it fits the SYK model extremely well, which is just the data I showed you a few minutes ago using exact diagonalization. They also measured the Fermi surface, or the Fermi energy, really. This is a random system. And again, they find that in the higher doping regime, you have a Fermi liquid behavior, and that totally breaks down once you enter the spin glass phase. And what they were also able to measure is the scattering time of the electrons, which was what was measured in the experiment that I showed you in the beginning. And they indeed find this 1 over T goes as KT over H bar, even with a coefficient, which is very close to what's seen in the latest angle-dependent magnetoresistance experiments. I'm not sure we should put that much significance to that. We need to really study how system-dependent that is before we get excited about that 1.4. Probably it's just an accident. Okay, so far I've just given you kind of empirical, numerical evidence that this TJ model has a critical point between the spin glass and the Fermi liquid, which has the basic physics, all the properties that you observe of the, somewhat artificial looking SYK model. But I haven't given you any understanding for why that is. And, the fully complete answer is we still don't have a complete understanding, but there's a certain limit where we do understand what's going on in the TJ model. And to obtain that limit, you have to take yet another large M limit. You have to take the SU2 spin symmetry and generalize to SUM. So there's a kind of a double scaling limit where you send N to infinity first and then M to infinity. And then you can solve this TJ model near the critical point. And you indeed find SYK behavior with all the properties I've just described, with exactly the same exponents and so on. And you can also compute things like the resistivity as a function of temperature in a lattice extension of the model. And it turns out it's linear in T. And the thing that's giving you this linear in T behavior is the same thing that gave us this linear in omega behavior here in the spin susceptibility, and that's the boundary graviton. Okay, so that's really the reason why I spent some time talking about the boundary graviton or the time reparameterization soft mode. That seems to be the crucial ingredient. It's a universal ingredient in all of these kind of SYK-like models. They all have this linear temperature or frequency dependence coming from the boundary graviton. And that is our conjecture explanation for the linearity resistivity, at least in this TJ model. But of course, we have to make it this random TJ model. It's not clear that the boundary graviton is present in, finite range models, but that's something we are studying these days. Okay, but at least in the model that we can solve, it's what gives you quite universally a linear dependence of resistivity and temperature down to zero temperature. Okay. All right, I think I have about 5 minutes or so left. Okay, I can't tell whether anybody's out there, but hopefully you can all hear me, and I can. Is that correct, Avad? I have about 5 minutes, 5-10 minutes.
Yes.
Yes,
that's
right.
You're here.
5 minutes. Yeah. Go ahead.
Okay, so let me just change gears completely now, or not really, as you'll see, and talk about black holes. Okay, just to give you some idea, why would we have this remarkable connection to black holes? Let me show you some actual data. This is a very recent paper this year, which was in PRL, which was highlighted in physics, from LIGO data, measuring mergers of black holes. And what they looked at was what's called the relaxation time. They have a way of defining it that you have to read this paper to find out why. But basically, it's the last stage of the merger of the two black holes in a binary system before they become a single black hole. So there's some kind of, and a single black hole, Hawking taught us, is a system in thermal equilibrium. Okay, so they measured it for a whole, it's not so easy to deduce it. You have to do some, from all the complicated data, some kind of fitting, and they did it for a bunch of gravity wave events. And what they find is that this time times pi is not so far from my favorite time, the Planckian time, h bar over kT, where T is the Hawking temperature of the black hole. Okay, so this is kind of an empirical observation at this point, but it's not as mysterious as the strange metal, because you can actually see from the Einstein's equation that this should be the time that's typical of any black hole. Okay, so that should at least give you, however, some idea of why there's a connection between black holes and quantum criticality. They all have this Planckian time. Okay, but let me just say, talk about black hole entropy, thermodynamics of black hole. So formally, what you'd want to do is evaluate this path integral. You take the action for Einstein gravity in t+1 space-time dimensions and integrate over gravity and whatever the other fields, compute the free energy, and then you get the entropy of a black hole background. Okay, so that's the very tall order. And in fact, one of the reasons the tall order, this whole integral is not even defined. It has all kinds of UV other divergences and so on. So it seems totally hopeless. Nevertheless, by a variety of arguments, and Gibbons and Hawking said, we could still make sense of this, at least at the saddle point level. We look at the saddle point of Einstein gravity for a black hole and just evaluate the saddle point action. And from the saddle point action and a consistent evaluation of the action, they claim that you got a saddle point estimate of the free energy and the entropy and all the other thermodynamic properties of the black hole. So that was 1977, where they boldly said, even though the integral is not well defined, maybe the saddle point still makes sense. So there's some corrections to the saddle point. Who knows what they are? They certainly didn't say what they were going to be. And from this type of, in the end, straightforward computation, they obtained the black hole entropy, the famous black hole entropy formula, which had been obtained by Hawking earlier by another set of arguments, where he got the same expression. So in natural units is the area of the horizon divided by 4 times g, which is Newton's constant. So what's remarkable about this is, of course, the fact that the entropy is proportional to the area, not the volume, as in any other quantum mechanical system. And today, I think this is understood from the fact that this entropy is really an entanglement entropy. So von Neumann entanglement entropy for the region inside and outside across the horizon. And the entanglement entropy goes very naturally as the area of the surface dividing the two regions. All right. So, but how do we, go beyond this Gibbons-Hawking result? So string theorists have learned how to do this and make sense of this, but only in the context of essentially supersymmetric theories of gravity, by the general idea of holography. So the idea there is that you can represent black holes because they have an entropy proportion to the area as a hologram, which lives in one lower dimension. And this system in one lower dimension is ordinary quantum many-body system without gravity. And therefore, its entropy will be proportional to its volume, and that would then capture, I'm just doing total injustice to a very deep and profound idea, capture the fact that the entropy of the black hole is proportional to the area, and in fact give you a computation with the Bekenstein-Hawking entropy. And this hologram is is a kind of a duality or a change of variables, where you don't integrate anymore over all of space-time, you integrate over this quantum many-body system. And then you can actually compute, in principle, all the corrections to the Bekenstein-Hawking formula, at least for supersymmetric black holes. Okay, so now today I want to argue and conclude that they can actually compute some of this for non-supersymmetric black holes, a very special type of non-supersymmetric black hole, though, which is charged. So you take a black hole that has a net charge. So you take theory of Maxwell's electromagnetism and Einstein's theory of general relativity, and look at solutions of these two equations, which is called so-called Reisner-Nordström solutions, which have a net charge. And one feature of the Reisner-Nordström solution is that as you go near the horizon of the black hole, you can ignore these transverse directions x, and the theory just becomes a theory of one space, zeta, and time. So you have a theory of gravity in 2D. Okay, so that's getting That should perk your ears because the SYK model was connected to 2D gravity, and indeed it is. So you can hypothesize that at least at low temperatures, I can focus on the near horizon region, not worry about all the UV divergences in 3+1 dimensions, go to 1+1. And so you can map quantitatively this theory to this theory, gravity in 1+1 dimension. In 2D, the metric in the Reisman-Nordstrom solution turns out to be ADS2. Okay, and then you apply holography to this. And so the hologram of a 1+1 dimensional gravity is a 0+1 dimensional model, 1 dimension lower, and that in fact turns out to be exactly the SYK model, the low energy theory of the SYK model, the gravity theory of this boundary graviton, the short chain I've shown you is in fact exactly this theory. So you can start from the SYK model, or you can start from the Einstein-Maxwell theory and end up with the same theory in between. Okay, so now I've told you, now we can compute this. Not we, but a lot of other people can compute it. And from that, you can in fact get a universal correction to the entropy of a charged black hole. So this is the Bekenstein-Hawking term at low temperatures at fixed Q. This has been known for a while, or never been written in this form. And then there's a correction, which depends on the temperature, the Hawking temperature. It's 3/2 log T. And this correction, in fact, is universal. It is correction that comes from the same boundary graviton of the Schwarzschild. Okay, and it's independent of all the UV structure that we don't know about. It's believed, that's of course a conjecture, but I believe it's a very reliable conjecture. Okay, so we've got the same central actor here, this time reparameterization mode gives a universal correction to the Bekenstein-Hawking entropy for any charged black hole in Einstein-Maxwell theory. All right, so let me conclude then. So the SYK model is a solvable model without quasi-particle excitation, exhibiting thermalization of many-body chaos in a time of order h power over kT. The low-energy theory of time reparameterization is the theory of the boundary graviton on 2D gravity on ADS2. I sketched how that happens, but didn't give you any details. Then we looked at a more realistic model, the random TJ model, which has a quantum phase transition from a metallic spin glass to Fermi liquid with some doping, just like the experiments. And near the critical point, at least in this model, the physics is very closely related to the SYK model. And then the boundary graviton, which is present in both of these models then, gives a lot of properties that are very interesting. It gives you this linear and omega correction to spin susceptibility, gives you linear field resistivity, and the universal corrections to the Bekenstein-Hawking entropy. Amazingly, these two facts are connected. Okay, thank you very much.
Thank you, Subir, for a very nice and broad talk, all the way from condensed matter fermions to black holes. Questions or comments for Subir? Maybe I can start. Two questions. One is, what is the applicability of SYK model to materials? Which different classes of materials does it apply to? Not just superconductors, but broadly speaking.
1 second, I can't see. Sorry. Oh, there you are. Okay.
Yeah.
What is the application of materials? Well, literally, I told you the model is a bunch of models with random hopping, and there's no material that's of that type. Wait a minute. Can you hear me?
Yes.
Okay.
Yes, we can hear.
Okay. But like I said, more broadly speaking, I would say that if you have a strange metal regime between a Fermi liquid and some kind of pseudo gap phase, which is present in many compounds, then there is some connection of this kind of physics of a doped mod insulator, if you wish, to the SYK model, and that's kind of what I argued in my talk today, at least for systems with some randomness in them. Now, there's been various proposals to build SYK models by taking graphene flakes with sufficient disorder, or taking a system with a flat band, putting in some disorder, and maybe you'll flow into some SYK regime. So that would be very interesting, and people are looking at experiments of that type. And there also needs to be a better theoretical understanding of, what is the domain of, I like to think of the SYK model as kind of some fixed point in some large space of models with lots of randomness and lots of strong interactions. But we don't really have an understanding of what is the domain of attraction of this fixed point. What I presented today was evidence that at least the random TJ model seems to be in the domain of attraction of this physics. But how broad is it? We don't really know. I mean, the difficulty is even theoretically, all these models with strong interactions are extremely hard to solve. You can't, diagonalize more than 20 particles, and there's a sign problem. So what I'm hoping that with some combination of experiments and theory, we'll understand this question better.
So my other question was, what is the evidence for charged black holes? Experimentally speaking, is there any evidence for charged?
Probably there's not. I mean, they're just solutions of Einstein's equation, and in fact, the low temperature limit is what's called the extremal limit. So no, I'm sure they're not out there. The reason being, in the actual universe, once you have the net charge of any astrophysical object is just neutral.
Hello. So we are
stable.
Yeah.
In the abstract, a charged black hole is a perfectly stable solution of Einstein's equations.
Okay. Thank you. Other questions or comments? There's a Philip.
Yeah, thanks, Subir. I guess I wanted to push you a little bit, just because it is remarkable that sort of the random TJ model with such long-range interactions seems to reproduce the sort of experimental phase diagram so well. And so I guess there does seem to be some sort of deeper reason. Sorry. I guess I was just trying to understand the parameter range for which the TJ model is supposed to apply to the Cooper rate seems so different than this random case, but yet the underlying physics seems to generate the same. And you surely have thought about what is generating that deeper connection, and I just wanted to push you on that. Could you comment on why just near neighbor, constant near neighbor hopping term would match?
Yeah. Well, okay. So I think I got the gist of your question because you were going in and out, but I assume you can all hear me clearly, though. So can I? Or do we need to reconnect in some way? I think I got the gist of your question for that. Okay. So the question, if I best understood it, is why the random PJ model should have anything to do with the real world. Just summarizing. Well, first of all, we're very happy that the TJ model captures some of the basic physics, like it has a pseudo-gap regime with spin glass order, and it has a Fermi liquid and a strange metal in between. But of course, if you look at the details of the pseudo-gap, like, is there charge order, or is there, these Fermi pockets and Fermi arcs and so on. Is really some kind of finite opening transition with Mach physics. So what we're keeping really is the Mach physics, the strong local interactions, but we're not keeping very well the spatial structure. Okay. But you can take some other models, not if you prefer, you could take a TJ model on a high dimensional lattice with nearest neighbor hopping and nearest neighbor exchange, and make approximations which are not fully controlled, and you'll end up with the same physics. You'll end up with the same model. So there's other sorts of limiting regimes when you get exactly the same solutions and the same physics. I just chose to talk about it in terms of the TJ model because it's the best characterized, and we know I'd rather talk about a given Hamiltonian that you can study and just by exact diagonalization rather than taking a large D limit, which you can't really study in any other way. So it's not just the random TJ model. There are also various DMFT-like regimes where you get exactly the same behavior with all of these characteristics. So, and I think it's still an open question, to what extent. I would say my guess would be as you get really near the critical point or at low temperatures, the spatial structure will become important. And we can't work with these random models anymore. But we don't understand really how low in temperature you have to go and what controls that. I think these are all open questions.
Thanks.
Other questions, comments?
I have a quick question.
Sure.
So about the SYK model, do you know if there are efforts to implement it in optical lattices?
There have been some proposals. I don't know of any efforts yet.
Okay, thank you.
All right.
It's a proposal taking some very complicated molecular arrangements with the random energy levels. Yeah, but I don't know of anybody who's actually trying to do that.
Martin, did you have a question?
Yeah, I asked it already.
Okay, you did.
Yeah, thank you.
Any other questions? If not, let's thank Subir for a very nice talk, and I wish you all, including Subir, a wonderful Memorial Day weekend. Everybody have a great weekend. Thank you so much. Subir will be in touch. Bye-bye.
Thank you. I enjoyed it. Thank you very much.
Bye-bye.